ROS developers, and welcome to a new open class. We are today in open class number 175. So hello there, everybody. And today we are going to be talking about Cartesian path planning, which is a specific method of motion planning. And we are going to be doing Cartesian planning with ROS2 and with MoveIt2. So yeah, welcome everybody to this class. I hope that you enjoyed it. And first of all, let me make sure that everything is all right, so that video is good, sound is good, you can hear me properly. Let me know here in the chat if everything is fine. And meanwhile, I'm going to go already to share my computer screen so that we can get started as soon as possible. So let me go there right now. Let's see. There we go. All right. So let me get here inside the class so that I can read your messages. All right. So I can see here Thomas, Florencio, Sonia, Lucian, Thomas Luke. Andres is saying that everything is good. Perfect. Excellent. Then we are ready to get started. So, as always, the very first thing that you need to do in order to be able to follow this class properly is to get a copy of the rosject for today's class. Yes. So in order to do this, in case that you are new to these open classes, it's very easy. All you have to do is to click here in this button that you are going to find right above the chat window here, which says fork and open the class rosject. So I'm going to click here myself to get a copy of today's class rosject. Then let me run it. So once you click on this button, basically two things are going to happen. First of all, as you can see, you are going to be redirected to the rosject page, which is this one. And here you are going to have in the right side the streaming area with the live video, the chat, in order to make questions and so on. So in my case, I'm going to move this to another window so that I gain some more space here in my screen for the project. Let me come here and open the chat here in a different shell. All right, then this is going to start loading. It might take some seconds to load. The rosject for today's class is a bit larger or bigger than usual. So yeah, just wait a few seconds and it's going to end up loading properly. Okay. Yes, an infinite loop of myself. Yeah, I have to mute myself, otherwise I would become crazy. So Thomas is saying, can I fork it later on? Yes, you can. I don't recommend it. So what I recommend, you already know, I always say the same, is that you get the rosject and you practice while I'm doing the class. Yeah, so now I'm going to start the class. I'm going to explain some things. I'm going to be doing some practical examples. And everything that I'm going to be doing is contained here inside the rosject. So you get an exact copy of the rosject I'm going to be using, which means that you are going to be able to reproduce everything that I'm going to be doing. Yeah, and I really believe, and we at the Construct believe, that the best way to learn is by doing, by practicing. Okay, so you are going to get much more of the class if you practice, if you do the exercises, if you run the programs with me, than rather just listening and watching to what I'm saying. Okay, but in any case, maybe for some reason you cannot work right now, I don't know, because you are in a mobile phone, whatever. Then in that case, yes, you can fork it later also. Yes, so Thomas says that that he doesn't have a PC right now. Yeah, in that case, yes, don't worry. You can listen and watch the class, and later when you are on a PC, you get a copy of the rosject and you practice everything by yourself. Yeah. Then let's go back to the rosject screen. So here I have mine. Let me close all this. Yeah. So once the rosject loads, as you can see here, what you are going to be able to see is the notebook. Yeah, the notebook for today's class, where basically here I have some explanation, some commands that you are going to be running, some code, etc. Everything is here in the notebook. Yeah, so this is the reference notes that I'm going to be following for today's class. So you have them also here in the notebook. All right. So I'm going to wait a few seconds to make sure that everybody has been able to get a copy of the rosject and has the rosject properly loaded. All right. So another thing is that you are going to get this rosject forever in your account. Yeah. So once you click on the fork and open the class rosject, you are going to be redirected here, but also you are going to get a copy of this project in your workspace, in your account, in your deconstruct account. Okay. So if you go here to the in the left menu to the My Rosject section, here you are going to find a copy of the rosject. Okay. So you are going to be able also to open or access this rosject tomorrow, next week, or next month, whenever you want. All right. Jason says, taking forever to load. Yeah, it might take, as I was saying before, maybe it takes a bit longer than usual because this is quite a big rosject. All right. Then just be patient and eventually it's going to end up loading. All right. So I'm going to take the chance to get a bit of coffee. Yeah, I have a bit of a cold, not to be worried about, but yeah, maybe my I'm going to be drinking during the class. Otherwise, I'm going to lose my voice probably. So yeah. All right. So let me know how is it going? Still loading the rosject? Has it loaded for somebody yet? Still waiting. Okay, still loading for Jason. Pepe, it has already loaded. Also for Gilbert, also for Dejan. Okay, so I can see that almost for everybody it has already loaded. So let's start. Let's get started with the class. All right. Then today, as I was saying in the introduction, we are going to be talking about Cartesian path planning with MoveIt2. All right. I don't know how much experience you have with MoveIt2 or with manipulation in general. Very interesting topic. However, today we are going to focus on this special motion planning, which is known as Cartesian planning. Okay, so there are some basic details about MoveIt2 and manipulation that we are not going to be covering in today's class. Okay, however, at the end of the class, also I'm going to remember that in case that you want to learn more about ROS2 manipulation, you can come here at the end of the notebook to the, you have a link here to the course in our academy about ROS2 manipulation basics, which basically here you are going to get all the knowledge from the beginning, okay? But for today's class, we are going to focus on this Cartesian path planning. What is this? Yeah, so why should I learn about Cartesian path planning and why should I be using it? This is the goal and what I'm going to try to explain in today's class. All right? Then, the very first thing that we are going to do is to launch a simulation. Yeah. So we at the Construct always explain things based on practice and based on real robotics examples, right? So today it's going to be no different, and we are going to be practicing with a simulated UR3 robot arm, like the one that you can see here in the image. Okay. Then, in order to launch the simulation, you have to run the command that you can find here in the notebook as well, right? So the very first thing that we are going to do is to start the simulation. So we are going to open a new terminal, a new shell here. And in order to open a new shell, you have to click here in bottom menu of your rosject page, you are going to find several icons. And the first one that you can see here, which says web shell, if you click here, this is going to open here a new terminal, a new empty terminal, okay? Then here, what we are going to do is to just copy the command from the notebook, yeah, and paste it here into the terminal, all right? And then just press enter, and the command is going to be executed. And basically this command, what it's doing is to start Gazebo and all the simulation processes here, so that we can have this simulated UR3 arm, okay? And also, as you can see, automatically, this is going to open a Gazebo window, like the one that you can see here, yeah? And there you go. So here we have the simulated UR3E robot arm that we are going to be using in today's class, all right? So the first time that you launch the simulation, it's going to take a bit longer. And even in some cases, it can happen that the robot arm is not properly loaded, okay? It might happen that it doesn't load properly, or that the controllers don't load, which is going to cause the arm to fall to the ground, okay? Then don't worry if that is the case. If you don't see the simulation like I am seeing here, with the robot arm here spawned in the center and standing still here, yeah? If maybe it can happen that you don't see the robot at all, or that you see the robot but it starts falling down to the ground, okay? If that is the case, don't worry. Sometimes the first time that you launch the simulation, there are some timeouts there in Gazebo that can cause these kind of problems. So in that case, don't worry. All you have to do is to just stop the process here with Control-C. You stop the simulation and you launch it again, all right? And then this second time is going to load properly, okay? So this second time you are going to be able to see the robot here spawned and standing still, which means that the controllers have been properly started as well, all right? Yep. So, so yeah, have we been able to launch the simulation? Yes. Andres says, took several minutes, but it finally loaded. All right, great. Great then. So what about the simulation? Have you been able to start it properly? Can you see it? Gilbert says, yes. Robot is in home position. Everything is smooth. Yes, ready. Awesome. Okay. So everything is going smooth so far in the class. That's awesome. Which means that, yeah, so we are ready to get started, right? Then, Cartesian path planning. So, have somebody here in the class heard about Cartesian path planning before? Do you know what this means? First time that you are hearing this Cartesian path planner? Any previous experience on this? Yes, no? Yes, yes, moving by axis. Used it in MoveIt in ROS1, says Amna. Yes, yes. All right, so Lu Jiang says no. Okay, then no worries. So we are going to explain this. So a Cartesian path refers to a sequence of points in 3D space that define a trajectory for the end effector of the robot, okay? What is the end effector? Well, the end effector is in this case, is the link where the gripper, let me go back here to simulation, try to show it properly, yeah? So the end effector of this manipulator is the link to which the gripper, yeah, in this case, this two-finger gripper that you can see here is attached. All right? Yeah. So the link to which the gripper is attached is the end effector of the manipulator. Okay. Then a Cartesian path refers to a sequence of points in 3D space that define a trajectory for this end effector of the robot in Cartesian coordinates, x, y, z. Okay? And each point along this path represents a specific position and orientation of the end effector. Right? And Cartesian paths are defined in the robot's workspace and are represented as a series of waypoints through which the end effector moves smoothly. Okay? So, in this case, my workspace is this world here. Yeah? So I could represent a series of waypoints in this space, in this workspace, as x, y, z points that I want my end effector to go through. Okay? We are going to see an example now, a practical example, okay? So in case that you are not fully understanding something, don't worry. Yeah? But imagine that here, so here, for instance, between the gripper, here you can see this white sphere, yes? This could represent a point in the workspace, represented by an x, y, and z position, yeah? Then imagine that I draw here more points, a series of points here in the space, yeah? So that would represent all the waypoints of a Cartesian path. Yeah? And all the waypoints I want my end effector to go through. Okay? And what does this imply? This implies that I have much more control over the end effector through the whole trajectory, through the whole Cartesian path. Yeah? So, when planning a Cartesian path, the robot moves from one point to another, from one waypoint to another, in a straight line, following a smooth trajectory in Cartesian space. What does this mean? This means that Cartesian paths are very particularly useful for tasks where the end effector needs to follow a specific trajectory. For instance, for painting, for welding, or 3D printing, or many more, yeah? So imagine that this arm and this gripper has to pick a cup of coffee, yeah? In order to move it from one place to another, yeah? So in that case, I want the cup to remain vertical at every moment through the trajectory, right? Because otherwise the coffee would be split out of the cup, yeah? So for these kind of trajectories where you want to have control at every moment over your end effector and the gripper, yeah, for these cases you would use Cartesian paths. Yeah? Does it make sense, more or less? Yeah? Do you understand more or less the purpose of a Cartesian path and why it is useful in manipulation? Yes? Okay. In any case, Andres says also yes. All right. In any case, this is very cool and very nice, but let's see an example, right? So the best way to actually learn this is by doing a practical example and seeing how this applies to a real case, to a real robotic scenario, right? So this is what we are going to do right now, okay? We are going to do an example based on an approach and retreat motion, okay? So what is a approach and retreat motion? Sorry. Well, these approach and retreat terms are used a lot in pick and place tasks, yeah? A pick and place task in manipulation means when a robot manipulator, a robotic arm like this one, picks an object from one place and places it in a different place. Yeah. So pick and place. You pick an object from one place, and you pick an object from one location, from one position, and you place it, yeah, in a different position. So this is known as a pick and place task. Yeah. And then for these pick and place tasks, we usually use this approach and retreat motions. Yeah. Why? Because usually you don't want to move the gripper to the exact position of the object that you want to pick, right? Because collisions can happen. You can end up breaking the object that you want to pick with the gripper and this kind of stuff. So usually what you do is to move the end effector to a position which is near in the surroundings of the object that you want to pick. Yes? You don't go to the exact position, but to a position which is near in the surroundings of the object. Yeah? And then once you are near the object, you do what is known as the approach motion. See? So this would be the first step, which is go near the object that we want to pick. Yeah? Then we do the approach, which is to actually get to the position of the object. Yeah? And then we would pick the object and do a retreat, which is going back to the original position. Yeah? This set of motions is what is known as the approach and retreat. Okay? And as you can see, for this, I want to have control over the position and orientation of the gripper, of my gripper, the whole time. Right? So what we are going to try to do now is to reproduce this approach and retreat sequence. All right? Yeah? So far, so good? Are you following? Yes? No? Pep Garcia says, sorry, I don't see the object in my simulation. Yes, in mine neither. So don't worry, Pep. Yeah, the object is not in the simulation, okay? For this, we don't really need the object. So the object is only here in these images in the notebook, okay? In the simulation, we don't have it. Okay, you could spawn it if you want, but it's not necessary for this example. All right, so don't worry. Put this here. I don't see. Yes, yes, yes. Why we don't independently? Okay, I don't understand this question, Altaf. It happened to me. Launch again. Oh, I understand the robot. Okay. I can move the view, but not the arm. Yes. Yeah, that's right. So here what you can do is to control the view of gazebo. Okay? In order to move the arm, we are going to have to execute some code now. Okay? Why we do it independently? Is there a way to do approach and retreat simultaneously? I still don't get what you mean, Altaf. So they are different motions. The approach is to get close to the object in order to pick it, and then once you have picked the object, retreat is going back to the original position. So no, it's not possible to do them simultaneously. They are different motions. All right. Then let's go to this example. So here we have a code, a C++ code, in order to reproduce this approach and retreat motions, okay? Now, in this code, we are using the typical motion planning methods, which is planning to an end-effector pose, and planning to a joint space configuration, okay, which are the two typical motion planning methods. All right. Then, in order to better visualize this code, actually what we are going to do is to open the code editor, all right, for the project. So here, if you go to the bottom menu, if you click on the second icon, the one which says code editor here, I'm going to click myself, this is going to open the code editor. Yeah, so this is going to give you, it's going to provide you a graphical interface in order to visualize all the different workspaces, folders, and files which are inside this rosject. Okay? So here inside the code editor, we can go to the ROS2 workspace and to the SRC folder. We click here to open it, and then here you are going to find this MoveIt2 scripts folder. This is a ROS2 package, okay? So if you open this package, inside the SRC folder, you are going to find these two C++ scripts. One is named approach_retreat, and the other one is named Cartesian_path. Okay? So the first one that we are going to be using and reviewing is this approach_retreat. Okay? So now you can double click here, and this is going to open here in the code editor the code, the file. All right? Now, here I'm going to explain a little bit what's going on in this program, okay? I'm not going to go into detail because that would be too much. And for that you have the course, the ROS2 manipulation course. But basically what we are doing here is to create a move group interface node, yeah? This move group interface allows us to communicate directly with MoveIt2 through a C++ API, okay? Then, basically here we are doing several things. So first of all, we are going to a home position setting a joint space goal. A joint space goal means that we set the position for every joint in the planning group. In this case, for every joint in the arm, we are specifying the position that we want it to go. Yeah? This is known as planning to a joint space goal in manipulation. Okay? So first of all, I'm going to a home position, yeah, using and setting directly position values for the joints of my arm. Yeah? Next, I am going to the progress position, or basically, which is the same, I'm going near the object, okay? And for this, I am setting a goal for the end-effector, yeah? So this is a position in space, as you can see, a position X, Y, Z, and orientation in quaternions, yeah? So I am specifying a pose, position, and orientation for my end-effector. And this pose is a point in the space, which in this example, basically it's here. It's right above the object. Yeah? So what I am saying is setting a point here right above the object, and I am setting this point as goal for my end-effector. Okay? Then, what else? So once I am near the object, in this case, above the object, I do the approach motion, okay? And for the approach motion, what I am doing basically is to change the Z coordinate of my end effector, and I am reducing this Z coordinate in a delta value. Okay, this delta is 0.04, which is basically 4 centimeters. Okay? Yeah? So I am saying, to the end effector. Okay, move down 4 centimeters, yeah? Because what I want is to move the end effector slightly down, as you can see here, yeah? So what I do is to change the Z coordinate, okay? In 4 centimeters. Then, once I am down, I do the opposite, which is the retreat motion. So instead of reducing the Z value of my end effector, I increase it, again in 4 centimeters, in order to go up again. Okay? Yeah? So, what I want to achieve, let me move here down, would be something like this. Yes? So, first of all, I go to the position near the object, which is this one, and then I move down and up again. Okay, this is the expected motion that I want to achieve. Yeah? So first of all, I go to a pose near the object, and then I do the approach and retreat. All right? Okay, and this is the code that I am using for it. All right? Then, let's execute this program and see what happens, yeah? So this is the first program, the approach and retreat CPP. Now, in order to execute it, we have to first start move group, yeah? So we have to first start MoveIt2. Then, for this, we are going to execute this command here. ROS2 launch, test MoveIt config, movegroup.launch.py. So, let me copy this command here from the notebook and go back to the terminal, and I'm going to open a second terminal here, okay? Don't close the first one, because here is where the simulation is running, yeah? So we are going to open a second terminal by clicking on this Add button here, and in this second one, we are going to execute MoveGroup. There we go. Okay, and now we have to execute another command here, which is to actually execute this code that we have just reviewed, okay? With this command, we are going to actually execute this code that we have just reviewed. So let me copy this second command and execute it in a third shell, yeah? So I'm going to open a third shell, a third terminal, and in this one, I'm going to execute this code. And let's see what happens, all right? There we go, so let's execute this, and now let me go to the simulation so that I can see what happens with the arm. There we go. Okay, so first of all, I can see the robot arm is going to the home position. Okay, this is the first motion. It's going to this home position. Now, second, the robot arm is going to plan a trajectory to go to a position near the object. Yeah, there you go. And now it should move down 4 centimeters and up 4 centimeters. Okay, but you can see that now it's starting to do strange things, right? So here it's like planning a strange trajectory. Let's see where it goes. Okay. So what the robot is doing right now is the approach motion, okay? There it's going. Okay, and now it should do the retreat, which is to move up. Okay, but again, the robot is starting to do some strange things, which is expected, okay? This is what I was expecting to happen. Okay, there we go, and there it is. Okay, and this is the retreat. So, what has happened in the example that we have just seen? So basically, the robot has moved to the home position, then it has moved right to the position which is above the object, and then instead of doing this motion, this simple motion, which is to move the end effector down, which is actually what I am asking the robot to do here, right? What I am doing is to slightly reduce the Z position of the end effector in 4 centimeters. Instead, the robot has started doing a strange motion, right? And the same for the retreat. Yeah? So why is this happening? Does somebody know why this is happening? Let me see here the comments. So, okay, a lot of questions here. Let's go step by step. So, Thomas is asking, so the first step is by what method of planning? Okay, this first step, the first step that we have seen, which is to move home, this is known as planning to a joint space, which means that you specify the positions of each of the joints of the planning group. Yeah? So this is one joint, this is another joint, this is another joint of my arm. Yeah? And here I specify the positions I want each joint. The goal position I want for each joint. This is the first method that we are using here. The second method is planning to an end effector pose, which is specifying a pose in the space that I want my end effector to go to. Okay, these are the two methods that we are using here, which are the typical ones used in MoveIt. Okay. Pep Garcia asks, what's the purpose again of the move group launch py? And Thomas answered, to launch move group interface. Well, actually, the purpose of launching move group is to start MoveIt, let's say. Yeah. So MoveIt is the main tool for manipulation, and in order to start MoveIt, we have to start the move group node. All right. Here we have Ricardo who is saying hello from MoveIt Day. Dejan, the code is in CPP file, and where we are launching py file. Yes, because in ROS2 the generic launch files are in Python always, independently of the code you are running. Okay. The Python is the move group interface, not the motion command cop. Okay, I don't understand this, Thomas. The path planning algorithm is samplet based. Kinematics maybe? Clear now, because the approaching given as desired point and not as movement in z-axis. Very well. Yeah. So Bart is right. Also, Dejan is right. So what is happening here is that actually, even though here I am specifying that I want to change the position in the z-axis, what I am really specifying is a point in the space for my end effector. So what is happening here? What is happening is that MoveIt is implementing inverse kinematics in order to reach this new goal. right? And because of this, the positions that are resulting from that are not the position, sorry, the trajectories that are resulting from that are very strange in most of the cases. Yes, because what I am doing here is not to specify a trajectory along the z-axis, but I am specifying a new point in the space. Yeah, so MoveIt, in this case, it's implementing inverse kinematic, it's computing inverse kinematics to reach this goal. And then the resulting trajectories for that can vary a lot. Yeah? So what can we do in order to avoid this kind of behavior? Well, what we can do is to use Cartesian path planning. Yeah, because in Cartesian path planning, we have explained that we can have much more control over the trajectory followed by the end effector, right? So, in order to solve this kind of issues, what we are going to do is to use Cartesian planning. All right? Let me go back here. That's not the issue. The EK is only computed for the last point. That behavior is due to the path planning algorithm. Yeah, sure. I mean, the path planning algorithm, which in this case it's an RRT, is the one that is generating the trajectory based on the point that I am providing. All right? But I don't have control over this over the trajectory that is being generated in this case, right? And Altaf here is how we deal with singularity, how we model it. I'm not sure I understand this question either, Altaf. In fact, the MoveIt Cartesian path is computing more EK as its implementation is a simple grid EK. Yeah, so maybe the words I used so the problem is not inverse kinematics, okay? The problem is that you don't have control over the trajectory which is being generated. Yeah? Not actually. The problem is not inverse kinematics, because inverse kinematics is needed for solving this kind of issues. All right. So it's not that inverse kinematics is a problem, but the problem is that I don't have control over the trajectory that is being generated. Okay. Then what we are going to do here is to actually change the implementation in order to compute a Cartesian path. Okay? Then for that we have this second approach, Cartesian path CPP. All right? Then this code we have it also here in the Cartesian Cartesian path.cpp script. Here in the code editor, you can access to it. All right? And here, basically, the code is very similar to this one, but we are changing in a couple of places. So you can see here first that we are going to the home position, where we are planning to adjoin the space, same as in the other approach. Then the first goal, we are planning to an end-effector pose. So we are specifying again the position and orientation for the end-effector. Okay? So far, this is the same as in the other script. And then here is where we start changing. Yeah. So for the approach in the previous example, what we were doing was to slightly change the pose of the end effector by reducing the position in the z-axis and specify delta and specify it amount. All right. Then here, we don't use this approach at all, but instead, what we are going to do is to use is to compute a Cartesian path by using this compute Cartesian path method from the Move Group Interface API. All right? Then how we do this? Well, here what we are doing is to, first of all, we generate a vector of poses, which we are naming approach waypoints. All right? Then we specify a waypoint, which is a target pose in the z-axis minus a specific amount. Okay? And we push this waypoint to the vector of poses. Okay? Then we add here a second waypoint, which is reducing the position in the z-axis, again, 3 centimeters. Okay? Then here we are disabling the jump threshold, and we are specifying an EF step of 1 centimeter, yeah, which is the distance between points of the Cartesian path trajectory. Yeah, what is the distance that we want between the points of this trajectory? And in this case, the maximum distance that we are setting is 1 centimeter. Okay, then we call this compute Cartesian path method, where we pass the waypoints vector with the end-effector poses, and we have to pass the EF step, the jump threshold, and this trajectory approach, which is going to contain the resulting trajectory. Okay, so given these waypoints, this function is going to generate the Cartesian path, the trajectory, which then I am using here, I am going to execute. All right? Then this is for the approach, and then for the retreat, we are basically doing the same, but instead of reducing the Z position, we are increasing it. Okay? So, let's have a look at this other implementation, which we can execute with the following command. So, let me copy the command from here, go back to the terminal, okay, to the third one. Yeah, remember, in the first one you have the simulation, and in the second one you have the move group node launched. Yeah. Then in this third one we are going to launch this Cartesian path launch file, which is going to start this the node which implements the Cartesian path for this. Okay. Then let's execute this. Let's go back to the simulation to visualize the results that we get in this second approach. I'm sorry. All right. Yeah, so first we are going to the home position using the joint space planning. Now we are going to the position, to the pose for the end effector near the object. There we go. And now is where we are going to do we are going to compute and execute the Cartesian paths for going down and for going back up. And as you can see, now we are getting the expected motion. Right? Which is very different of what we were getting previously. Okay? And this is because we are using, in this case, Cartesian path. We are computing a Cartesian path, which provides us much more control over the trajectory of our end effector. You may say purchasing this link. Oh, cool. So Ignacio has shared here a link about Cartesian planners. Yeah, however, this is for MoveIt1. If I'm not wrong, for MoveIt2, for instance, Descartes, I think it's not ported to ROS2 yet, to MoveIt2. Needed MoveIt Servo. So yeah, eventually they are going to be ported, but so far I think that they are not yet ported to ROS2. All these Cartesian path planners, which are more sophisticated. Yeah. Cool. Better than the first one, jumping around. Yeah, sure. Why we moved the arm minus 0.03, then another 0 in Z for approaching? Well, this is just to generate a trajectory in the Z axis, AMNA. So you can change these values if you want. So you can change these values to 0.2. I don't know. Okay. So this is just some waypoints that you are setting here for the Cartesian path to follow. Okay. Why there are two target poses pushed for each case? Well, this is just to have some waypoints in our vector. Okay, so you can add more here if you want. You can add you could add more waypoints here. Yeah, so this is just an example, a simple example, let's say, where with a couple of waypoints we can already achieve the motion. But for more complex motions, for instance, if you would like to draw something here in the ground, for things like that, I mean, you could add as many waypoints as you want here. Okay? Why on the approach we subtract a delta of 0.04, while at second one we subtract? Yeah, so this is just values, okay? So here these are just examples. So for instance, if you want, you can put 0.2 and 0.2, which is going to it's going to finally be the same, okay? So here we have 0.4. And if we put a waypoint at 0.2 and another waypoint at 0.2, we are going to end up having we are going to end up having the same distance. Okay. So these are just values. So the thing here is that you can provide waypoints for the trajectory to follow. Yes, correct, Amna. Yes, so if you split it into, if you just specify one waypoint with a distance of 6 centimeters, then you have less control over the end effector positions. Okay, if you specify two waypoints over a trajectory over the z-axis, then you have more control over the trajectory that the end effector is going to follow. So yes, you can say that it's for smoothness of motion. Yes. So path planning guarantees, if you use Cartesian paths, guarantees straight lines between waypoints. That's correct, Lu Jiang. Yes. Yeah, does it make sense? So here, yeah, I mean, you could add also, you could do like this. So you could do 0.03, but all these things, what you should do is to test them, okay? So the reason why I provide this project to you is that you have all these available for you to try, yeah? So so what you should do now is to investigate for yourself, yeah? So what happens if I remove one waypoint? Is this still going to work? Yes, no? Yes? So what happens if I want to draw an X here in the ground? How would I do it? What waypoints should I specify here? Yeah? So all these, I encourage you to try it, okay? This is why I provide this rosject for you to have, yeah? So that you can actually now have this code and you can try, okay? Which is how you are going to really learn, rather than watching this open class, which is going to give you the basic notions only, okay? Yeah? Does it make sense? And I have seen here also, I am sorry, because I have seen some questions here from some people like, what is this move group? What is this move group that we are launching here? Yeah, so all these, I have not explained it in this open class because of time limitations. Actually, we are already at the time limit for the open class. But in case that you want to learn more about move group, what is this move group? What are we actually launching here? Or what is this test movie config package? How have you created it? Yeah. So all these is explained much more in detail here in the course. Okay. Here in the ROS2 manipulation basics, all this is explained from the beginning, from how to create a MoveIt2 configuration package, motion, all the different types of motion plannings, Cartesian paths also, how to include perception into the manipulation pipeline, etc. All right? Yeah? So, okay, I think I'm going to leave it here. So thanks to all of you for attending this class. I hope that you enjoyed it. I hope that you have learned something new and that you use this project to test a little bit on your own and to do your own research. So yeah, thanks a lot for being here with me. And yeah, so I will see you again next Tuesday with another open class. I hope to see you all again there. And until then, as always, keep pushing your ROS learning. Bye-bye.